Hello, everyone, and welcome back to another Planetarium show. My name is Jessica. I'm the director of the Planetarium, and with me tonight are two familiar faces if you've been here before. They're two students who work at the Planetarium, and I will let them introduce themselves, starting with Eli.
Hi, I'm Eli. I'm a physics and astronomy undergraduate at UMD.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
So, tonight we have a really fun show for you. If you have visited us in person, a year and a half ago, you may remember we had this program called Mythbusters Astronomy. And we decided that it was time for it to have an update. And so this is kind of a preview of the new version of that show, which we are calling Astronomy Fact or Fiction, which takes a look at common thoughts, some misconceptions, some are correct, and takes a look at all of these different ideas and is kind of a fun game of what do you know about astronomy? And do you get these right or wrong? So before I completely spoil everything, I'm going to turn it over to Eli. But of course, as always, if you have any questions throughout the show tonight, feel free to leave them down in the comments. I will keep an eye out for those and we'll ask Eli as they come up. We'll also have time at the end to answer those questions as well. So with that, Eli, it's all yours.
Hey, give me a second. I'm gonna have to set up my windows here, make sure they look all right. Also, I don't know how practical it is, but if you want to put your answers in the chat, you can do that. But the delay might make that a little tough, so do it on your honor. No cheating. Um,
This is where if Facebook polls wasn't so laggy, we could totally have done that.
yeah, yeah, and the kind of the way. Hold on, let me make sure screen sharing works. Does that look okay?
Yep.
Okay, awesome. And yeah, like the way we're gonna be spinning it once we're in the planetarium is going to be like kind of like a trivia game that we play with the guests at the planetarium. So if you kind of want to play it that way, keep your own score, tell us what you got at the end, you can go ahead and do that. So, all right, astronomy, fact, or fiction. I've been talking long enough. Question number one. True or false? The moon has a permanently dark side. And I guess I'll allow a little bit for people to come up with their answers. All right, let's see. False. There's no such thing as a dark side of the moon, contrary to popular belief and one of the seminal rock albums of I'm sure that was the 70s. Um, So let's take a look at why. The reason people often believe that there is a dark side of the moon is because there is what's called a far side of the moon. We on Earth are kind of always viewing the same side of the moon, which we call the near side, and then the opposite side is obviously called the far side. And for a long portion of history, we didn't know anything about that side because we couldn't look at it. And the first time we saw that side was when an Apollo mission circled around the moon and they were able to view it. So for a long portion of human history, that side was shrouded in mystery, and therefore the name dark took hold, albeit incorrectly. Um, it's kind of similar to the misnomer. Well, I guess it's not a misnomer, but the name dark matter. We call it dark because it's like mysterious and we don't know much about it, much like this far side of the moon. It's not inherently dark as far as we know, or at least it doesn't emit light. So I guess that does make it kind of dark. But it's also called dark just because we don't know anything about it. The reason there is a far side of the moon is because of something called tidal locking, which basically means that because of a long history of gravitational interactions between the moon and the moon rotates once, exactly once for every orbit that it makes around the Earth. Um, and you can kind of see this here in this diagram. So if there was no rotation or no tidal locking, you can you see my cursor? So if the red side were one side of the moon, like we see one side with the craters and stuff, and then the purple side doesn't have any craters. We would see the red side, but then we would also see the purple side because the moon isn't rotating. But on the right, when we see that the moon is rotating, since it's rotating at a rate such that it turns around once for every time it orbits the Earth, the same side is always facing the Earth. And we can also view the next slide, which kind of gives a video of this. So the way that I kind of like to think of it is, look at where these craters are. They're kind of on one half, or along the curve of one side of the moon. Those curves are always facing the Earth, and they always end up in the same spot after one rotation. So say like at the top here, okay, they're pointed straight down. Now as the moon orbits and rotates, once it reaches the top again, they're pointed straight down in this image. So that's just kind of a visualization of why we always see the same side. So no, there's no dark side of the moon. There is a far side of the moon, and I think it's just that far side of the moon that has been shrouded in mystery for so long that gave the idea of a dark side of the moon, but we don't actually have one. The moon is illuminated from all sides at different points in its orbit around the Earth. Okay. Next question. True or false? The astronauts on the International Space Station experience zero gravity. Give another couple seconds. Alrighty. That is false. While it may appear that astronauts are completely untethered by Earth's pull, NASA actually found a way to work around it, and that pun was intended, and you will understand more in the next few slides. So this is a really good video that kind of explains conceptually why this happens, albeit not for the ISS, but just for objects orbiting the Earth.
To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
We're going to scrub a little bit to a later part of the video. There we go.
Imagine that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity.
All right, so that's just kind of a little example of this orbital motion and a thought experiment that Newton came up with. So kind of a little more deep dive into it. The cannonball seen in Newton's cannon thought experiment is analogous to objects orbiting the Earth. They are falling to Earth along the curvature of the planet, and gravity is keeping them in orbit. So in the image on the right, the red arrow can be thought of as a combination between gravity and it's like the balance between the cannonball's forward motion and the motion caused by gravity, which would pull it downwards. This is kind of given by Newton's first law of motion. An object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an outside force. The white arrow pointing forward is the forward motion of the satellite, and the white arrow pointing downwards, this is in both images, the white arrow pointing downwards is the downwards motion due to gravity, and that red arrow is the combination of those two motions, which at very certain speeds causes it to be an orbit rather than it falling and reaching the surface of the planet. So we can see that gravity plays a huge part in the motion of the International Space Station. In fact, the gravity up there is just about 90% of the gravity that we experience down here. It's just that the ISS is falling towards Earth around the Earth, I feel like is probably the best way to describe it. For astronauts inside of the International Space Station, this means weightlessness. As the ISS is falling just the same as they are, there's nothing like resisting their fall towards the Earth, which is what we perceive as weight. So when you're standing on the surface, the Earth kind of pushing back on you and resisting your motion towards the center is what we perceive as weight. But when there's nothing pushing back on the astronauts because the ISS is falling like around them, they don't really perceive any weight. They're still being pulled by gravity. It's just that that gravity isn't resulting in them being resisted by anything because they're falling around the Earth. Alrighty, next question. Okay, true or false? The sun is an orangish, yellowish color. I'll give a couple of seconds. Well, yep, I accidentally put the answer up, but
It's fine. So sorry, I started talking before I unmuted myself on the stream.
okay.
But we did just get a question. How is the correct speed and height calculated? I forgot my physics and math.
Yeah,
And
there's oh, I'm trying to remember what it's called.
circular velocity is the square root of gm over r.
Yep. Yeah. So for the interesting thing is that for every height above the surface of the Earth, there is a velocity that would cause the object to orbit the planet. It's just that the farther you get, the weaker gravity is pulling you, so the weaker you need to, or the slower you need to be moving forward to counteract that. But if you were, 5 feet above the surface, you would need to be moving extremely fast to not be kind of careened by gravity to hit the ground. So there is a velocity for every radius outwards from the surface.
Yep.
But I'm not remembering. I'm sure it's just like a like Jessica said, just a permutation on the gravity between two objects.
Yeah, it's balance of energy.
Yeah,
It comes
it's,
from balance.
Specific example, the ISS is traveling at 17,500 miles per hour. That speed puts it at its distance away from the Earth that
Right.
it is.
Right.
If it were any other speed, then its distance from Earth would be different.
Right.
Yep.
Yeah, it's something like v equals the square root of like
gm over r.
Oh wait, it's v equals the square root of gm over r.
Uh-huh.
Oh, I actually wait. Did you say that before?
I said that earlier.
Okay, well, I'm just gonna still assume that I remembered it off the top of my head to make myself feel better. But
short version of the answer is physics.
yeah, yep. Okay, well, you guys know the answer to this one already. False. The sun is actually not an orange-yellow star. The sun emits light in all colors, which combine to be a whitish star. First, before this, I think we should talk about light a little bit. Light comes in these little packages called photons, and photons, I'm sure you've heard, behave a lot like waves and particles, but we're going to talk about that wave part now. They have a characteristic called a wavelength, which is the distance between two sequential crests or troughs. So the distance between this point and this point would be the wavelength of the light, and wavelength determines the properties. So a small range of wavelengths is the visible light spectrum, and this means that we can see light with wavelengths from 1/100th of a micrometer to 10 micrometers. So visible light is, like I said, this very, very small portion right here in the wavelength spectrum. And now we should talk about how wavelength pertains to light. And I tried my best to make this kind of scale and look correct. But the hotter an object gets, the smaller wavelength the light that comes off of it has, or the more energetic the light is. So cool stars like red dwarfs have surface temperatures of about 3,000 Kelvin, have a peak wavelength of about 750 nanometers, which is very red. Hotter stars like our sun with surface temp of 5,300 degrees Kelvin or something like that. Jessica, I think you know it off your head. What's the sun's?
Sun is, I think, 5,700.
5,700. Okay. Well, somewhere in the 5,000 Kelvin, peaks at about 550 nanometers, which is kind of in the middle, and that results in like a combination of a lot of light, which turns into white. And even hotter stars like blue giants peak at 450 nanometers, so very, very small wavelength light, which is blue. And here's a picture of the sun from space. The only reason we see colorful skies and a colorful sun here on Earth is that our atmosphere scatters a lot of the light. So depending on the time of day, different colors will come through, and we'll see, an orangish or yellowish, while the rest of the colors have scattered off of our atmosphere. But when there's no atmosphere impeding light from reaching you, it's a combination of a lot of wavelengths of light, and that combination turns into white. I mean, just like you've heard, if you shine a white light through a prism, the prism scatters it into the rainbow. It's kind of the reverse. The rainbow comes out the sun, and then it hits your eye, and your sun sees that as white. So talking a little bit more about how the atmosphere plays a part in this, blue light is really easily scattered by our atmosphere, and that's just because of the particles that are in our atmosphere, just the composition of it. So when the blue light is scattered, it zips around through the sky until it comes down to your eye, making the atmosphere appear blue. And it's actually like literally bouncing off the sky, like it's bouncing through the air molecules that are in the sky, and then sometimes it's just aimed perfectly so that it goes right in your eye. And direct sunlight, which is that kind of light yellowish, makes it through directly, which is why when you look at the sun, which you shouldn't do directly, but when you see the sun, maybe off to the side or something like that, you see it as that kind of yellowish color, because the blue light has been scattered off, and depending on the time of day, more red or less red will make it through. So that's why like in the evening, there's more atmosphere for the light to go through, so more red gets, or more, how does it go? Less of the red gets scattered, so you see that kind of orangish yellowish sun, but then during the day, you get that kind of white yellow light. And it just depends on the angle that the light hits the atmosphere, when it's more shallow, when less light gets scattered, and that determines the color you see. So I kind of stumbled my way through that one. Okay. True or false? A light year is a measurement of distance. Wait a little bit here. Alrighty. That is true. A light year is defined as the distance light travels in a year in a vacuum. So light, like we said, is made out of these photons, these little particles or wave packets, and these photons move at a finite speed. In a vacuum, this speed is 299,792,458 meters per second, or 671 million miles per hour. The light year is how far a photon would go if it traveled at the speed unobstructed for one Earth year. And that speed changes when it enters different things like water or air, but in a vacuum where there's no air or water or anything to obstruct it, it travels at that speed. So just a little bit of quick math here. If light travels at 671 million miles per hour, and there are 24 hours in a day, and there are 365 days in a year. You see that number there. That is, hold on, let me do 587 trillion miles a year, so extremely far. Like I said, that's an extremely long distance and gets super messy to write out for objects extremely far away if you're to represent it in miles. So instead we use light years. Even the closest star is over 4 light years away, so writing that out again just gets really messy and really inefficient. So to make that easier, we use the light year. And there's an even bigger unit than the light year for distances even further, which is a parsec, which is, how many light years is a parsec? 3 something?
3.26.
3.26. There you go.
Which actually, we just got a comment asking about, they say Star Trek's, but I'm assuming Star Wars misuse of a parsec.
Yeah.
Which is actually something we cover in our Star Wars Fact or Fiction show.
Yeah. So I don't know. Should I talk about it here, or I mean, I've got it in my head. I've talked.
Yeah, go ahead.
Yeah. So I'm assuming that they're talking about the Millennium Falcon made the Kessel Run in however many parsecs. I'm guessing that's what they're talking about, because I don't know when else they talk about parsecs in Star Wars. And it's not actually an incorrect usage. It's actually correct. It's just that they don't really give you the context to understand why. The reason it's correct is the Kessel Run is a region of space where there's a lot of black holes. And so out of caution, a lot of spacefaring vehicles would just take like a super huge detour around the Kessel Run, or around that region of space with the black holes, and it would just take a really long time because it was just a huge detour. But what Han was saying when he said that it made the Kessel Run, I think it's 12 parsecs, he says. What he's saying is that his ship is so fast that it was able to, rather than take a detour, just like zigzag right in between the black holes and make it super quick. So it is actually it's fair game. They used it right. They just don't really tell you why.
So they are saying they did mean Star Trek. I don't know a lot about Star Trek. Lindsay, do you know anything about Star Trek's use of parsec?
I've never seen Star Trek.
No. I've seen some Star Trek, but I can't remember parsec usage right now.
All right, I might do a little bit of Googling while Eli continues.
Yep, sorry, I just kind of did a big Star Wars dump on you. I apologize. And this is just kind of a cool little reference here. When light is traveling at that speed in space, you can see the time it takes to reach different objects. So the sun to the Earth is 8 minutes, it's 8 light minutes in distance, which means that it takes light 8 minutes to get here. So the really interesting thing is that you actually don't see the sunrise for 8 minutes after it's already happened, because it's taken that long for the light to get to you. So we're kind of on a delay when we're seeing the sun. So it should be 8 minutes further in the sky, or it is 8 minutes further in the sky, but we're seeing it as it was 8 minutes ago. Kind of interesting. Earth to Alpha Centauri, which is one of the closer stars to us, 4.5 light years just about. So it takes 4.5 years for light to get from that star to us. Again, pretty crazy. Earth to the far side of the Milky Way, that's 52,000 light years. So like hypothetically, if there was a planet on that other side of the galaxy that we were looking at and we saw it, that planet could be gone. Like we would not know for 52,000 years because it takes that long for the light to get to us. So it's kind of an interesting implication, especially when you're looking at other galaxies. The closest galaxy, it takes 2.5 million years for that light to get to us. So kind of mind-boggling. Okay, this one's really fun. And I had a lot of fun working on this one. Okay, true or false? It's much easier to balance eggs on the equinox. And I had never heard of this one previous to seeing the show. I'd never heard about balancing eggs on the equinox, but it's pretty interesting. So, all right, final answers in. This one is false. The position of the Earth around the sun has a completely negligible effect on your ability to balance an egg. Rather, it's probably just hard because eggs are really hard to balance because they're an awkward shape. In 1945, Life magazine published an article explaining a craze of egg balancing, taking the Chinese city of Chongqing, I believe I pronounced that correct, by storm. Upon the beginning of the Chinese solar term, people would balance these eggs on the ground, believing that the solar system was aligned such that balancing the egg would be significantly easier due to some gravitational alignment or something. After the article was published, it caught on like wildfire in the US, and people started doing it all the time on the spring equinox, which like kind of makes sense when you think about it, but it doesn't actually do anything. So an equinox is basically just the day where the sun is directly overhead of the equator, which doesn't even make sense for anybody that doesn't live on the equator in the first place. So if we in Duluth were to follow that logic, the sun would have to be directly above Duluth, which actually never happens. So it doesn't even really work for anyone that's not within the tropics. So I did a little bit of math for this one, which is fun. So let's imagine a hypothetical situation where the sun is directly overhead. So let's say we're at the equator and it's an equinox. If the sun were directly overhead, an average sized egg, about 2 ounces in mass, the gravitational force it would exert on that egg would be 0.06% as strong as the force exerted on it by Earth. That's, like I said, negligible and would not contribute to the motion of the egg. Now let's assume that it's not the equinox. Assuming that the egg is 2 ounces in weight and is sitting on a plywood table, which is important, the force of friction between it and the table that prevents it from rolling away is over 112 times stronger than the force of gravity were it acting sideways on the egg. So, like I said, gravity would not influence that egg's motion and it would remain upright if you were able to balance it, which is really hard. So the difficulty of balancing the egg does not come with where the gravity is pulling it. It comes with that awkward shape, and assuming a perfectly rounded egg, you would have to find the exact bottom of the egg to balance it on, which is 1 point on the egg surface. So in conclusion, it is possible but extremely difficult to balance an egg on any day of the year. but it's going to be equally difficult on every other day of the year. Although a little trick I learned when putting this together, when people would do it as like a show to other people, they would sprinkle salt on the table to add a little bit of give that would support the egg. So if you want to impress people and cheat a little bit, sprinkle salt on the table and then try to balance it on the salt. Okay, true,
Real
false.
quick.
Oh yeah.
So I did a little bit of Googling.
Yep.
And I haven't found anything major that Star Trek did other than getting if you do calculations based off of what they said, the distance of a parsec is different than what it actually is. So like their parsec in the show is like a much smaller unit of distance than a real parsec. That's all I've been able to find so far. But
Interesting. Somebody did their homework. Or
fact.
didn't do their homework. Okay, true or false? NASA spent millions researching space pens while the Russians used pencils. Story that I think a lot of people get told. That is false. Both began using pencils in space and then bought space pens independently developed by another company. So they're like the big ruse is that Russia gave their astronauts pencils when NASA wasted millions of dollars making some like space pen. It's actually not true. They both started using pencils. But they realized that like the little bits of graphite or lead that would come off the pencil and like the little bits of wood were really bad for the space stations they were in, and it like would clog air filters and stuff, and like also it's potentially toxic for you. So they stopped doing it. While the story is funny and kind of popular, the pencils used by Americans didn't come cheap, because when they realized that the pencils were like breaking and stuff, they had to like they went through a bunch of phases of development making mechanical pencils, and then eventually turned into a pen. And those mechanical pencils were just under $130 a pop. So, whoa. And then NASA spent $5,000 on mechanical pencils, which the public didn't smile on. I don't know why this is. There we go. So this is just a little diagram of the famous space pen. Fisher Pen spent over $1 million developing this space pen, and it was money well spent. NASA and the Soviet space program both invested in the pens, buying them for a much more reasonable $2.98 per pen, but they bought them in bulk, so I would assume Fisher Pens made their money back. And not only does it allow the user to write in microgravity in extreme temperatures or underwater, or on Greece, which seems impossible, but it was also used by Apollo 11 astronauts to return to Earth safely. This is kind of an insane story. As one of the astronauts was climbing it back into the lunar module, their life support pack hit and broke the switch that engaged the lunar module's engine that would return them to Earth. And the other thing is that before they had gotten back in the lunar module, they dumped all their tools and stuff out on the moon, so their spacecraft was lighter to launch back, and they couldn't go get them. So they were just kind of stuck. But after some quick thinking by NASA scientists and the astronauts alike, they jammed a space pen into the thing and flipped the switch, and successfully made it home. So that's kind of terrifying to me, but also very interesting that they used their pen to save their lives. Okay, here we go. This is not going. True or false? Moon phases are caused by Earth casting a shadow on the moon. All right, cast your votes. I realize that we're running over time very quickly, so I'm going to try to go a little faster. All right, false. Moon phases are caused by the moon's position around the Earth relative to the sun, not by the Earth casting a shadow. While it isn't unreasonable to think that the Earth is casting a shadow on the moon, which it actually does sometimes, there is a lot more at play here. So let's think about where the moon is around the Earth. If one half of the moon is always illuminated, which is true except during eclipses, and we are seeing none of the illuminated side, where would you think it would be? If you thought about it in terms of Earth casting a shadow, you would think that it would be directly behind the Earth relative to the sun, because the shadow cast by the Earth would be covering the moon. But in fact, when we don't see any of the moon, when we're not seeing any of the illuminated side, it's in between the Earth and the sun. So As seen in this diagram, the phases of the moon change as the moon orbits the Earth, and at the new moon phase, Earth is seeing the side facing away from the sun, which is obviously not receiving any of the sunlight. That's what we're looking at right here, and that's what we see as dark. At full moon, over here, the fully illuminated side is facing the Earth, and the illuminated side is facing away. And this is just kind of a good little animation, I think, that shows this. Alrighty, so that's probably enough. So there we are. When the sun, or when the moon is directly in between the Earth and the sun, the fully illuminated side is facing completely away from the Earth. We're not seeing any of it, so we're seeing the not illuminated side. I was about to say dark side, but then I realized that might
I was going to
confuse
say,
people about the
this also calls back to that very first one. You can see here that the far side of the moon is fully lit up at this point.
Right, right. But just to add a little bit more, the Earth's shadow does impact the moon sometimes, but this is called an eclipse, not a new moon. This also doesn't happen every month. It happens twice a year. And this is because the Earth's, or the moon's orbit around the Earth is tilted relative to the ecliptic plane, which is the apparent path that the sun takes through the sky. And because of that, there are only 2 points where the moon and the sun are kind of on the same level. And the specific requirements for a lunar eclipse are that the moon is at one of the nodes, and that the node is either in between the sun and the Earth, which is what a solar eclipse is, or on the opposite side of the Earth from the sun, which is what a lunar eclipse is. And just go back. It's just that shadow that gets casted by the Earth onto the moon that causes it to go dark for a little while, which is what that eclipse is. Alrighty, next question. True or false? Black holes pull everything in. Give you a second to cast your votes. That is false. So the idea that black holes violently commandeer anything more powerfully than objects of the same mass is a pretty big misconception. Black holes are extremely compact collections of mass, and they're so dense that the escape speed at the surface is greater than the speed of light, making it impossible for anything with mass to escape. And I shouldn't say surface because that isn't exactly correct. There's almost like a virtual surface created where the escape speed, and that surface is where the escape speed becomes greater than light, and that's called the event horizon. But this does not mean that all similar mass objects have the same properties, only things as compact as black holes do. So we're going to watch a short video on what would happen if the sun were replaced by a
like
black
that
hole.
motion. Now look at the sun. It is not currently a black hole. We can change that. What we need to do is compress the sun. So let's lock its mass so that it doesn't change while we make its radius smaller. Let's make its radius as small as we can. And, oh, where'd it go? Well, it's still there. It's just become a black hole. Pretty spooky. But now, let's look at the rest of the solar system. All right, zooming out. And, nothing's changed. I mean, something's changed. It's colder and darker, but nothing's flying off into space or getting sucked in. You see, by shrinking the sun, we didn't change the direction of down for the planets. They're always being pulled by gravity towards its middle, and making it smaller didn't move where the middle was. But also, the strength of that force pulling them to the middle of the sun stayed the same.
Alrighty, so first of all, love Vsauce. If you guys aren't watching Vsauce, I would highly recommend that you do. That little mysterious music that kicks in whenever he says something intriguing always gets me. Just to kind of elaborate on this, the gravitational pull an object exerts on another object only depends on, well, let's just say the gravitational pull an object exerts only depends on that object's mass, not the type of mass or how physically large the object is. Because of this, a solar mass black hole at the center of the solar system would do the exact same thing as the sun does, except for warm us up and keep us alive. The only difference happens if you get really close to the black hole. Since black holes are so dense, you can get so much closer to the center of mass than you could if it were the sun before colliding with anything. And this has some very dastardly effects once you make a near approach. So the closer you are to an object's center of mass, the stronger the gravitational attraction becomes between it and you. So then, since you get much closer to the black hole center of mass, which is called the singularity, the gravity becomes much, much stronger. And you reach that point where the escape velocity is greater than the speed of light, which is what makes a black hole so interesting and unique. So yeah, and that blue line just represents how much closer you can get to the black hole's center of mass before you collide with anything. So if it were a sun mass black hole, assume these two spheres are the same mass, you could only get to here before you collided with something. But with the black hole, you can get to here, and gravity got much, much stronger because according to this equation, which is what describes how strong gravity is between two objects, the closer you get to something, the stronger the force gets by a very large amount. So increasing your closeness to the center of the object by that much affects the strength of gravity a lot. When a black hole begins to devour, say, something like a star, it begins by pulling the star's mass into a ring around itself called the accretion disk, which is this kind of illuminated disk you're seeing here. The accretion disk is a very flat ring of extremely fast moving material that becomes really hot and emits X-rays. Most of this material actually makes its way out of the accretion disk, whether it be due to collisions with other accreting objects or irregularities in the black hole's shape that cause gravitational differences between locations in the disk. Astronomers actually predict that up to 90% of material that enters the accretion disk leaves it as well. So no, black holes don't violently devour everything that comes within its reach. In order to be devoured, objects have to enter the event horizon, which is seemingly unlikely even if you make a close approach. And here's a kind of a diagram of the black hole. So the event horizon is denoted by this arrow here. It's this area right here. So if you were to pass that point, you are getting sucked in, but you can remain in a stable orbit around that point and not get sucked in as long as you're going fast enough, much like we were talking about the orbit of the ISS around the Earth, except for a black hole, the gravity is going to be really strong, so you're going to need to go really fast. Alrighty, we'll go to the next one. Okay, true or false? Winter happens when Earth is further from the sun. This is actually false. Winter happens when the area of the Earth you are on is tilted away from the sun. Its proximity to the sun actually doesn't bear any effect on it. So remember earlier how we talked about during the evening, light from the sun has more atmosphere to travel through than it does during the day, and it scatters a lot more. Well, the same goes for winter, kind of. During winter, the sun's rays hit the atmosphere at a really shallow angle and are therefore spread out over a much, much larger area. Because of this, the heat is stretched out very thin and it gets colder. There's just not as much heat coming from the sun hitting a specific area of the Earth's surface. So in summer, the light strikes almost head on and is much more concentrated, resulting in those higher temperatures. So you can see here during the winter, the northern hemisphere, which is where we are just for this example, is tilted away from the sun. So there's much less light hitting it and it's hitting it at a much shallower angle. But then during the summer, we're tilted closer to head on and much more light hits our area and it hits at a much more direct angle. So it has less atmosphere to travel through. That's just how that works. Interestingly enough, the Earth is actually closest to the sun during winter, and that's kind of coincidental, but just based on where the Earth is when winter happens for us, the Earth is just a little bit closer to the sun. So the days when the Earth is tilted the furthest towards the sun are the solstices. We talked about this a little bit already, and these are the longest day of the year, and the equinoxes are the days when the sun's light is evenly distributed between the two hemispheres. So the winter solstice is when the northern hemisphere is tilted furthest away from the sun and it's getting the least amount of heat, which is why that's the colder part of the year. Alrighty, here we go. True or false? Adding a small amount of mass to Jupiter would make it a star. Just a second to get your answers in. This is false too. In order for Jupiter to become a star, you'd need to add about 80 more of its own mass to it to make it a star. The concept is not like totally unreasonable, however. Technically, you could add enough mass to any object for it to become a star. The only catch is that the majority of this mass has to be hydrogen, as stars use hydrogen as fuel throughout most of their life, or a good portion of their life. So saying that you could add a bunch of mass to a baseball for it to become a star is technically true, but it doesn't really work like that in the real world. The reason why so many people think that Jupiter is what they call a failed star is because Jupiter is close in size to some stars and is made mostly of hydrogen. In Jupiter's case, like I said, it would have to be 80 times its current mass to become a red dwarf star, which is the lightest type of star. And if 80 Jupiters were mashed together, it probably would become a star. Because Jupiter is mostly hydrogen. It's like 90% or something, 92%, something like that. And then the star could begin fusion at its core, which is what makes it a star. So while Jupiter is close in volume to some stars, it's so far off in mass that it's not, like I said, it's not unreasonable. The concept isn't unreasonable, but Jupiter is very far from becoming a star. This is kind of interesting. I thought this is a size comparison between the two bodies. So Proxima Centauri is the star that's closest to Earth, or the Sun. Sun is technically the star that's closest to Earth, and that's Jupiter. But that's a mass comparison. As you can see, like I said before, you'd have to add 80 more Jupiters for the star to ignite.
So some of the, I think this is, you presented like this really well, by the way. But I think it's interesting to think about, a lot of people don't think about the fact that if you just add more gas to something, gas compresses really easily.
Yeah.
So it's not actually, if you add a bunch more mass to Jupiter, it's not actually going to physically in size get that much bigger. It's just going to be squeezed more, and everything in it is going to be denser.
Yeah.
And so I think it's that kind of understanding of it may be similar in size, but if you add more, it's not actually going to grow in size much.
Right. Yeah. And people have been like really scared about this for some time because some of the compounds that are in Jupiter are extremely flammable. And so people have been scared, like, if something hits Jupiter and the friction starts a fire, it's going to turn into a star and like burn us, or it's going to blow up or something like that. And that's not true, because we've actually seen stuff hit Jupiter and it has like sparked and nothing really happened. We've seen it happen a lot, and although the collisions do end with impacts that impart a lot more energy than any artificial explosion we can make here on Earth, as soon as the hydrogen and helium dust settles, it's kind of all back to normal. This image is the comet Schumacher-Levy 9 colliding in Jupiter, and this collision released more energy than like atomic bombs, and there was still no ignition in Jupiter's atmosphere, so we got nothing to worry about. We're safe.
Also, stars aren't big balls of fire.
Right. Okay, last one. And I know this might hurt Jessica a little bit, but true or false, Pluto got demoted to being a dwarf planet because it is small. All right, one last chance to cast in your votes. This is false. The International Astronomical Union, or the IAU, has 3 simple criteria to determine what is a planet and what is not a planet, and they are: the body orbits a star. In the solar system's case, it orbits the sun. The body has sufficient mass to maintain a spherical shape, and the body is gravitationally dominant by a significant amount in its local region of space around the star. Okay, let's look at which ones Pluto satisfies. Pluto orbits the sun, we're good there. Pluto is a sphere, so we're good there. Pluto has not cleared its area in space. Actually, oops, I accidentally went backwards. Close to the orbit of Pluto lie a lot of objects called Kuiper Belt objects, such as dwarf planets Eris and Sedna, that rival the size and mass of Pluto and have not been cleared of Pluto's vicinity of gravitational influence. So thus, these objects were deemed dwarf planets, including Pluto. So the IAU currently recognizes 5 dwarf planets in the solar system, with a few more waiting on determination. So there we go. That is all I have. I'm sorry, that one's so long. I apologize. But that is Astronomy Fact or Fiction.
Yeah, that was good. And part of it is we ended up with, a little mini Star Wars discussion there in the middle.
Mm-hmm. Yep.
But yeah, it's actually interesting. Those, I think there are 10 candidate dwarf planets right now. And they're candidates because we're waiting to see their shape. We're waiting to see if they are spherical. If they are, they'll be dwarf planets. If they're not, they're Kuiper belt objects. And yes, it hurts me a little bit. Pluto was a planet growing up, when I was growing up, okay? It was my favorite planet, and at least there's some saving grace in that Pluto is the largest of the dwarf planets. So it is king of its category, and I will take that.
It's a big fish in a little pond, rather than the little fish in the big pond.
All right. So I am not seeing any questions at the moment. There was this was great. So kudos to Eli. He's done amazing work on revamping the show here. And obviously what you're seeing here is kind of a simplified, like flat screen version, but when we open back up, we will have this in its full dome glory. So you can come and check that out. I don't know, Eli, are you going to do custom animations for this too, like you did for Star Wars?
I'm gonna sure try if the computer will let me.
Yeah. Oh yeah, we're moving the new one in there, so.
Yeah, so that's what I'm
Yeah.
here for.
Awesome. All right. Well,
Yeah,
if there,
I'm gonna toot my own horn for a second here. Watch the Star Wars one when we reopen, because I made a custom, like, you know, like the wall of text, the scrolling text. I made my own one of those, and I'm really bad with computers, but I made my own one, so you should come check it out.
he learned a lot of awesome stuff to make that Star Wars show great, and we are so excited to hopefully be open maybe by the end of summer and be able to show you that brand new show, which I don't think we've had the Star Wars show in the dome for 3 years.
Has it really been that long? No, we did it when I got in.
It's been okay. It's been more, maybe 2.5.
Yeah, something like that.
Because I think we pulled it not long after I started, because it needed a polish. It needed a revamping, especially with all the new stuff that's come out.
I'm gonna try to find a Jedi costume and like a toy lightsaber to wear for the first time we do it too.
You will be required to wear that every time.
Yeah, yep, that's fine. I wear it at home sometimes anyway. Around the house.
All right. So I am not seeing questions. If anyone does have any last questions, now is a great time to leave them down in the comments. And while we give that a minute to see if anything comes through, let me tell you what's coming up over the next week. I have to remind myself that it is Wednesday and not Saturday. So on Saturday, we are going to take you on a tour of our solar system, go and visit all of the planets up close and learn some great things about them. It's been a while since we've done this show, so we thought it would be fun to do it again. Next Wednesday will be another edition of Ask an Astronomer. And so you can come and ask us all of your astronomy questions that you have. Maybe your goal is to learn something new. Maybe your goal is to try and stump us and see if there's anything we can't answer. But come by and ask us those questions. We'll also talk about some cool current events that are going on in astronomy as well. And then next Saturday is our next edition of our exploration series, where we're going to take an up-close look at Venus, one of our neighbor planets. And we chose Venus for this exploration series because of the announcement from NASA that came out. Has it been a week ago? Maybe 2 weeks ago? About some exciting new stuff happening with Venus. And so we thought, why not? Seems like a great time to talk about it. And it is kind of a fascinating planet. So yeah, that is our upcoming week.
Sweet.
All right. Well, no questions, so we will wrap it up here. Thank you everyone so much for joining us. Of course, thank you to Eli for the work that has gone into creating this new show. We hope you enjoyed it and will come check us out again. We are streaming regularly throughout the summer at our normal time, Wednesdays and Saturdays at 7 p.m. Central. And so we'll be doing that through the summer and until we reopen again, which we don't have a date for you yet, but hopefully we'll have some news on that soon. All right, well, have a wonderful evening, everyone, and we will see you again next time. Bye.